Right, hello and welcome. Thanks for so many of you turning up for the talk. Tobias, you probably already know Tobias, but I'm here to introduce him. But given the crowd, I think his reputation precedes him. Delighted that Tobias has joined us in Cambridge as a permanent member of staff back in October and brought a big chunk of his research team here. He does fascinating work. This is a very broad talk. The longer title covered so many different topics. It's amazing where compilation intersects with things. But without further ado, I'll pass straight over to Tobias.
Yeah, thank you so much. And thank you everyone for showing up. I'm quite too excited to talk a little bit about my research and actually see so many faces here. As Simon just said, I'm new to Cambridge. Many of my students are new here. So it's really amazing to see and get to know people here in Cambridge and some of the other people coming from London and Oxford. I talk today about the compilation game, which really is me trying to organize kind of the maybe a little bit seemingly disorganized research that we're doing in my research group. So we're touching a lot of different fields of computer science systems, and I tend to believe that there's some kind of connecting story behind all of that, but I kind of struggle to verbalize that. So I guess today this is my attempt to verbalize what we're actually doing, why we are doing it. Obviously feedback is very much appreciated. To give you a little bit kind of set this into context, I want to actually start with something that is not really compilers. I'm starting with a picture of a space rocket, and let's ignore that this is produced by Elon Musk, which is controversial and stuff, but the point I want to make is that certain industries which had radical change in terms of productivity. So in SpaceX, for example, they introduced internet all over the world just a couple of years ago, and I never thought when I grew up that this would be possible. Not sure if that's desirable, but it's kind of the things which I thought was a radical change. Elon is a little bit crazy. He wants to have humans on Mars. I'm still not sure that will happen. But what I want to say is, in certain industries, there are very radical changes, right? In the space travel, one of the reasons for this radical change was that the cost of moving a kilogram of material into space reduced by over 100x over the last couple of years, right? Pretty much from 1960 to the 2000s, there was no change in how much it costs to move stuff to space. And then in a couple of years, it radically dropped. One of the reasons for this space travel, just as an example, was that the way these spacecrafts were manufactured was very different. They moved from very specialized engines to a large number of smaller engines where you need to produce hundreds of these engines per year to make the spaceship fly. But you realize that you can't craft the engines one by one manually, but you really need to introduce automation into that system, right? And so a lot of as this kind of motivational slide, what was changed is there's a lot of reuse and a lot of automation that really radically dropped the cost of space travel, right? And so I want to kind of connect this a little bit with the compiler ecosystem, where maybe many of you identify as compiler developers, which I would claim are highly specialized engineers, experts at crafting the most powerful compiler. But I ask a little bit, do we all need to be experts? Do we all handcraft our compilers one by one? Or is there a way to kind of commoditize a little bit how compilers are developed? And for that, I'd like to look a little bit at compilers themselves, right? So a compiler for me is a C compiler. GCC and LVM, the most prominent open source compilers. Probably we have several LVM, GCC developers here in the room. That is a compiler, right? And an instance of that compiler might be Swift, Rust, all these kind of static compilers. But I want to make the case that our compilers are so much more. I see some people here working on formal methods, SMT solvers. It's just rewrite engines that reason about expressions that need to be optimized. In some way, that is a compiler, right? Some of you do really hard formal methods, interactive theorem improving, Isabelle, Coq, Lean. Internally, these tools have a lot of the technology that a compiler typically has, right? If anybody cares about cat pictures, right? AI, all the domain-specific languages that drive cat pictures in the world are in some way compilers, right? Or, I mean, some of you may worry about climate change. You can also use the same technology for climate change. with less of a profit, but maybe more of an impact. And hardware design, right? Writing Verilog, using Verilog to build the chips that power your devices. I mean, I thought always hardware design is really difficult. That's nothing for me as a software engineer, until a former PhD student working with me told me it's actually just a compiler. So he attended my compiler lecture and said, what we do internally is just a compiler. So I want to make the case that all these things really are compilers, and we should maximize reuse across all these pieces of software. I realized when I was thinking about that it's pretty much not possible. All of these tools are like individual software projects, very independent. Everybody kind of has a developer, every tool has a developer community that prides themselves of being expert in EDA tool design, but it's very rare that people move across these ecosystems, right? But if you look behind the back, you realize they all actually are just abstractions. Abstractions that are somehow interconnected, better interconnected within a tool, and then through a lot of like hurdles, you kind of cross these barriers and then kind of connect tools, right? So we had a research project, I talk about it later, defining better ways to interconnect these abstractions. And a lot of the research we do in my research group covers abstractions within these different ecosystems. So that's what I call the compilation game. And the rest of the lecture, I want to make the case what this compilation game really is. Right? So to be slightly more structured, for me a compilation game consists of a board, like a board game, chess, which are pretty much the intermediate representations, the abstractions that we have in a compiler. And there may be very different ones. There may be one for hardware design, there may be one for quantum computing. All these kind of abstractions are different instances of a game. And each game comes with its own rules and moves. Rules are pretty much the semantics of these languages, and the moves that you have in the game are the transformations that satisfy your semantics, kind of that preserve the semantics of your game. We talk a little bit about game objectives, so different metrics that we have in a compiler, which are the metrics we want to optimize in our game. And someone asked me, how did I come up with compilation game? And I think, I don't talk a lot about AI in this talk, but part of that inspiration was looking at tools like AlphaGo, for example, where you had these large games that were played. And I was asking myself, I'm not an AI researcher, right? I don't know how these things work. But I feel like our compilers are not gamified. They are way too monolithic, way too large C++ code bases. It's really hard to kind of break them down into pieces and kind of, in some way, destroy them to recombine them into something that's more scalable. And so I'd like to talk about intermediate languages, intermediate representations. I give you a very brief pitch, probably a little rushed, through the history of compilers, starting 2010. I mean, all the other stuff is really important, but let's start at 2010. So we had plenty of C++ compilers. Some of them started here in Cambridge. The ARM compiler, for example, was like a really good specialized compiler. Intel had their own compiler, IBM, PGI, HP, GCC and LVM, some open source compilers. How many compilers do you think exist today, kind of used in production? And I might be wrong, but kind of my impression. Any bets? C++? Yeah. What's your bet? 1. So my answer is 2.5. So there's GCC. Most of the commercial compilers now are based on LVM. I may have missed 1 or 2 that exist, and I think Microsoft Visual C++ is still kind of not LVM or GCC based, and so it's half because it's not open source. But it's a very, very good compiler, and probably I miss a couple of others, but the large number of the commercial compilers moved to LVM. Why did they do this? I mean, they realized there's a lot of synergy that you can exploit. There's a very classical compiler picture, C++ to an intermediate language to backends. And it's not just C++. Many compilers realized that the load store, arithmetic-based intermediate representation is really all they care about. And suddenly a lot of programming languages built themselves on top of LVM. But very quickly people realized a load store is really too low level to optimize Swift, Rust, Julia, so we introduced new abstractions. I started my PhD and I realized loop optimization needs its own abstraction. And so suddenly you realize this universal IR already is broken a couple of years ago. And this kind of only got worse. domain-specific compilers introduced their own abstractions. We moved some of our loop optimizations into some of these deep learning compilers. What I want you to feel is that we're like playing with like building abstractions, reconnecting abstractions all the time, right? And that's something that not just the LVM community, but that became highly popular. And the typical recipe for anyone who worked with LVM was, I take domain knowledge, I build a custom IR, I make it look like LVM, I maybe even reuse LVM's data structure, I still kind of re-implement most of the other things, and I lower to LVM. That's how you build a domain-specific compiler, kind of LVM style over the last 10 years. 4 or 5 years ago, the community asked themselves, can we avoid this cost? People at Google, with Chris Latner, Albert Cohen, built a tool called MLIR, which automated that process. So instead of a new compiler, you now have something called a dialect, which is just an instance of an IR. In the MLIR compiler, all these things got auto-generated or reused, and typically would still lower to LVM. That is a big improvement in terms of like engineering development. Just over the first 1 or 2 years, a lot of abstractions, a lot of operations were introduced into that ecosystem. So there was a lot of activity. And that just to remember that LVM and GCC for pretty much their existence had one universal IR. Right? Just over the last couple of 4 or 5 years, this like number of IRs really exploded. So I put a little battery pack there just to say that this kind of really powers what happens in compilers. And what also changed is a little bit how compilers are built. We go away from kind of this serial lowering from C++ to LVM to x86 to really like a tree of abstractions where a lot of the lowering starts to mix a lot more modular abstractions. Right? And that's what happened, I would guess, 4 years ago, and then a lot of community development happened in that space. So for the LVM community, it was clear. Initially, it took roughly a year to build a new compiler IR. With MLIR, everything was almost perfect. It took roughly 3 months for a seasoned compiler engineer to build a new IR. I think that was a major improvement, right? So I was really happy. I was an LVM developer. I went to all my friends in Switzerland to the climate scientists and said, now we can build climate compilers. Let's get started. I gave them a workshop 3 days, trying to convince them that LVM is the greatest thing. And they were deeply disappointed. It was incredibly painful for them to build their own IR, and 3 days was by far not enough to get anywhere. Right? So from their perspective, compiler development is still a craft where you kind of build your own thing. It's incredibly painful, remains painful, right? And so one of the things we introduced here was this IRDL language, which started to really crack the compiler open as a way that we move away from C++ as the defining language and start to make a lot of the abstractions declarative within our, particularly in this case, the MLIR compiler ecosystem. That's something MLIR already set out to, and we're kind of just trying to accelerate that trend. But now I talk a lot about IRs. What are actually intermediate languages? And here we can slow down a little bit and have a very simple example of, in this case, an MLIR-based intermediate language. The syntax is kind of verbose and not particularly beautiful, but it's very explicit. It really just indicates we have a function with 2 arguments which have a given type, and this function executes 2 operations that belong into some dialect or namespace. Right? And what a compiler really does is it harvests a lot of domain knowledge, in this case about complex numbers, and knows that computing a multiplication over complex numbers followed by a norm might not be as efficient as computing the norm first and then multiplying the non-complex result. Right? That might be an optimization that might be a piece of domain knowledge you are aware of as a domain expert in complex number theory, and you want to add that to your compiler. And the first thing you go ahead to develop that, for example, in MLIR, this is kind of a little bit over the top, is you implement your dialects, which historically was a lot of C++ code, then written in a domain-specific language called TableGen. But the point I want to make, it was relatively complicated. This is the pure C++ code, so you can probably make it more concise, but it was relatively complicated and not as introspectable. So with IRDL, we introduced, interestingly, a meta-IR, so an IR that describes IRs, that can be used to pretty much define all the different abstractions within a compiler, as well as tooling for language servers, statistics, refactoring tools. And that is interesting, first, that you can actually do that. But also just looking at the IR, again, it's not particularly beautiful. It's very explicit. But you see that just you give the dialect a name, a namespace in some way, you define a type and the two operations, and pretty much that's what you need to get the initial example type checked in some way in the MLI compiler. You need slightly more for the operations, so mostly the number of operands and results, as well as the type variable, and a little bit of documentation and formatting. So in just 2 slides, we implemented our own compiler. And that's what I wanted to kind of show my friends from climate science years back in Switzerland. It could actually be that easy, right? You don't need to struggle with all these other things just to communicate an abstraction that you want the MLI ecosystem to understand. We also looked at the existing dialect in the ecosystem because many people struggled and built those. And interestingly, just a simple statistic gathering how many operations, for example, does the LVM dialect have, which is around 100, or like the linear algebra abstraction, which has roughly 10 operations. It's just a statistic I wanted to get. But just getting that out of the existing compiler infrastructure is actually a non-trivial project. If you have a declarative representation, you can do that easily. We also realized the types in MLIR, in fact, are mostly declarative in the sense they are so simple that you can describe them with a domain-specific language. Not all of them. Some need kind of Turing-complete escape hatches. But the majority of what the LVM community does is structurally not very complicated, right? And so I think I tried to make the point that over the last 5 to 10 years, there was really an incredible amount of people putting their time into developing abstractions that are shared within compilers. But interestingly, the other thing that the MLIR community, the LVM compiler community does is we really don't have an idea about what the compiler IRs actually mean. Kind of compiler IRs for us are structural representations of what happens within a compiler. But a lot of what is a legal transformation, what is actually the meaning of this structural representation is pretty much, if you really want to understand it, you better ask the person implementing it or maybe read some of the documentation. So I know here some people in the room do really formal work, and they have this astonished look on their face when I explain to them, we don't really know what our IRs mean. I mean, we have a rough idea of what it does, and we kind of, if we reach a disagreement, we might decide to discuss the kind of dark corners of our semantics, but kind of fully defining semantics seems to be not as urgent of a priority. And so we started with some students here to think about how can we define semantics for this MLI ecosystem. And so, MLI really has no formal, somehow informal semantics, but we started to think how can we define those. And interesting. And so pretty much there are 2 choices. We can go for an interactive 3 improver like Lean, which is incredibly expressive, but requires some manual input to really define semantics, and in particular, demonstrate equivalence between certain constructs. Or we can use an SMT-based semantics, which can be automated or can be used to automatically check equivalence, but is certainly a lot less expressive. And so we started to see using both these tools, can we actually find a way to introduce formal semantics into a compiler ecosystem, which for very, very good reasons doesn't formally define what we are doing, right? And so it's just a sneak preview in one of the tasks that sometimes comes up in our compiler. We might have a simple rewrite from an addition to an XOR where we want to prove correctness, right? The typical LVM approach is we send a pad review and write a sentence and say that's correct. That typically is accepted, except if it's a really difficult transformation, then people discuss for 2 days and then they agree or disagree. But obviously, sometimes that goes wrong. And it actually takes quite a lot of time to reach agreement, right? And so what we wanted to have is a tool where you pretty much just copy-paste the IR before and after the transformation, and then some magic happens. And what you get is a mathematical statement of a strongly formalized equality that needs to hold for that rewrite above to be sensible, right? And then we built a lot of tooling to make this kind of parsing LLVM into a theorem prover actually work. We derive a couple of theorems that the source and the target IR are related. These theorems then are given to tactics that simplify all the MLIR boilerplate, and in the end, we pretty much just need to prove the theorem that you just saw. If that holds, we have a formal proof that our rewrite is correct. This is incredibly generic, but still a little bit complicated because you manually need to prove this kind of theorem. And you can do that for any kind of dialect. So in this case, we might have an IR with an addition and a constant, and we can define type signatures, denotations. And so for local rewrites, for almost any domain, we can now give semantics to part of the MLI ecosystem. We also have an SMT-based approach. We pretty much take the same people rewrites. Sometimes for analysis, we actually can synthesize the code that implements what LVM or MLIR does. But we also translate them into an SMT dialect. Interestingly, yet another IR, which we can optimize using compiler technology to make the queries to the SMT solver simpler and faster. And then we use an SMT solver to check correctness and precision. Here, two very brief examples. On the left-hand side is an incredibly verbose way of defining people rewrites in MLIR. On the right-hand side is our translation into an SMT query. If that is interpreted, this right-hand side query will tell you if the rewrite on the left-hand side, so x plus y turned to y plus x, actually happens to be correct. And for plus, that is in fact the case. We can do that also for analysis, so any kind of data flow analysis. You can define that as a compiler IR. We can translate it to an SMT query. And again, we can prove correctness and equivalency. The interesting thing is what I want to show here, and I'm not sure if it becomes or is very obvious to you. A lot of these things that I just present are not radically new. But I think the way we're doing that, like using really compiler rewrites from one IR to another, actually is quite unconventional. Typically, you would call into Z3, where there's a kind of a C++ library call, and it works. But there are really cool research projects you can do where you can start inlining across tools, optimizing SMT expressions using pre-existing MLIR global value numbering, which just with a classical setup is very, very hard. I wanted to very briefly talk about metrics, just to kind of complete the game. We just submitted a paper to PLDI. Our objective was to analyze the cache performance of a deep neural network. Deep neural networks are complicated. Let's start with something slightly simpler. Cholesky, for example. How many of you believe they understand the computational complexity of that code? Give it a guess. Roughly. My guess is that most people in the room have a rough idea what's the computational complexity of that code. But if I ask you what's the percentage of cache misses of that code, what's the most expensive memory access, or how many capacity misses does this code have, my claim is that most people in the room have no idea, including myself. So I gave that presentation a couple of months ago, and I still don't know the answer. But if I give you the cache sizes and the cache line size, we can execute it, and we know that there's actually relatively low number of cache misses. This is the most expensive memory access, and we can give you precise statistics over these properties, right? And it's interesting. For certain structural properties of a program, we have a very good intuitions. For others, it's almost impossible to understand what that actually means. And this was just a simple kernel, not Matmul, but Cholesky. Deep neural networks are a lot larger. And so if people keep optimizing deep neural networks, it would be really useful to understand how does a code transformation affect the cache behavior of a program. Because cache behavior, in fact, is quite a good performance proxy, right? And so classical approach is profiling. You profile your deep neural network. It takes 20 minutes. You have a coffee. If you appreciate coffee, when you like the coffee in the department, for example, this is a really good use of your time. If you either don't drink coffee or you're slightly agitated after profiling for a day, you're realizing that maybe a tool like we call it MLIR MEMinfo, which kind of analytically can predict the cache behavior, might actually be quite convenient. And so I don't go through the entire implementation. If you're interested, we can talk about that offline. But But in the end, it's really relatively simple. You can have a shell or like a command line tool that goes over an MLI program, and for every kind of operation, it will annotate you the miss rate and the percentage of number of memory accesses that are executed at that statement. Right? This is really like just a sneak preview of some of the tools currently developed in our research group. But what's interesting and kind of, there's one paper already published and then one more that's potentially coming up. What's interesting is this is kind of, by doing it analytically, you can be asymptotically fast in predicting cache behavior. Because you don't need to analyze the full program, step by step, each memory access, but you can reason in summary over the structure of the program. Right? A really interesting story. We can maybe chat later about it. Compared to a pre-existing tool, we are a lot faster. In particular, previously, most tools just timed out for many kind of large-scale deep neural networks. This is like just very recently we started to manage to pretty much give you cache mispredictions for arbitrary networks from this like vision benchmarks. This is just like a single data point. I think it's interesting to see kind of, I guess, at which kind of level we reason in a compiler about like the performance or the metric of programs. So historically, when I started my PhD and I was doing loop optimization and I was implementing a loop optimizer and I said, great, I need to find the tile size. So I look in research papers, how do I find the right tile size? And pretty much the answer was the compiler had no idea. It had a scheduling model of like the backend instruction, the pipeline model, that's pretty much the analytical model it had. But any kind of memory behavior was way beyond the scope of what you could do in a compiler. And I think we are just now reaching the threshold where we kind of model a full deep neural network. We have all the like abstract structure of that network, and we can actually, analytically fast tell you how fast is that thing, right? And so now bringing back this like analogy of the compilation game, right? You have abstractions, you have rewrites, you have in theory like which rewrites are correct, and you start to have metrics that scale to some of the problems you care about. This somehow reminds me a little bit of AlphaGo and these kind of things. I still have no idea about AI, but I think we are like moving towards something where like humans can collaborate better, and maybe automatic tooling can start collaborating on that game. Talking about productivity and collaborating on these things, I made the point that all of you should, in some way, like explore something like LVM, MLIR, and these kind of tools. But I also told you that you need to invest 3 months of your life to get started, right? So some of you may like to be by themselves and enjoy quiet time. Other people may value family time and don't want to sacrifice their family. So making this process faster is important. I just moved here from Edinburgh, and I was asked to give a compiler lecture there. And I said, I want to teach students the compilers that industry uses today. And so I thought I want to teach them MLIR, and we started with one student on the summer, see if they successfully can implement a couple of courseworks in MLIR, and a very, very motivated and bright student, but I think we incredibly failed. It didn't work. It was just like implementing everything, installing it, it was just so much overhead just to get started. And the core concepts are actually not really hard. SSA, blocks, regions, abstractions, pretty much half of what I discussed today and a little bit more. And people rewrites. It's relatively simple. And then we have TableGen, CMake, C++ templates, a lot of compile time, and you realize that actually the kind of core ideas are simple, but you can't reach them, right? And so what we came up with, we built a tool that we now call XDSL, which is really just kind of a deep copy of MLIR. There's no innovation in that space at all. We just re-implemented everything in Python, made it accessible, really interconnected XDSL, and I think here we called it still PyKick. We connected closely with MLIR, and now you can work with a lot of the concepts without having to pay the price. But you can switch over to a full C++ production quality infrastructure at the point when I don't know, you develop a product that you want to commercialize, or you scale to data center scale, the moment where you need that scalability, right? So if anyone coincidentally happens to be here also for a compiler social afterwards, has like some food or something and wants to chat and try some stuff out. A pip install with XDSL takes a couple of seconds instead of an hour. The install size is a couple of megabytes instead of a gigabyte, and the download size itself is also a couple of megabytes. Meanwhile, we installed a couple of dependencies. Maybe it's a little bit larger. But the point is, before I think it was unrealistic to have a apple juice chat with a friend and kind of try something out over these things. I think today that may not be so unrealistic anymore. So we teach compilers in Edinburgh. We used it to teach this flow, a coursework from Chocopy, a Python dialect, down to RISC-V. Worked quite well, 150 students. Most of them finished that coursework, and they really built an end-to-end compiler for this specific subset of Python, using pretty much the infrastructure I just presented throughout this presentation. It's also quite useful if you want to prototype your compiler features. You don't need to kind of have upstream quality code from the get-go. You can just start prototyping an idea, another idea, and if one of your 10 ideas maybe actually makes sense, and then you can consider how to actually implement it in a more robust way. So for us, that was really something that improved productivity quite a lot. So I'm just presenting here one slide of a talented intern here who wanted to visualize some compiler transformations. So it's just some command line GUI tool to optimize this piece of code. And so on the left-hand side, you have the input. Then you choose the optimizations. On the right-hand side, you have the output. There's this really fun condense button, which just runs each of the passes and see if it actually has an effect on your IR, and then eliminates whatever really is not meaningful. I mean, it's a small project at the beginning, but I think at the beginning of maybe an even larger vision. But the point is, building such a thing with MLIR would have been way more complicated, right? And this is just something, I mean, just running all the passes over all the different IRs and I mean, making it work was conceptually maybe difficult to figure out, but actually the implementation-wise, infrastructure-wise, I think was really only possible with the kind of infrastructure we built. So yeah, try XDSL out if you like it. And I want to kind of close this talk with like one instance of the game, which I found really interesting like 2 or 3 years ago, where I had no idea about hardware design. And then Fabian came to me and then handed our compiler lecture and said, by the way, I started prototyping a hardware compiler. And I've thought it's interesting. And a couple of weeks, 1 or 2 months later, we submitted it to PLDI and it got accepted. So it's quite interesting. So what's the story about hardware design? Right, hardware design is pretty much Verilog and VHDL. And that is a rough approximation. There are a lot of like high-level languages which pretty much are just Verilog. So let's assume hardware design is Verilog. And then hardware design on the back-end side, if you have a simulator, a synthesizer, an equivalence checker, verifier, all these kind of tools. Remembering the C++ ecosystem 15 years ago, they are all proprietary, redundant, complex, inaccessible, and don't scale very well. That's not entirely true. There are tools like Yosys and Slang that are open source, but kind of overall, there's not this dominance of an open source infrastructure that we see in the C++ compiler world. So what we did here is we kind of introduced multiple levels of IRs, unsurprisingly, one for the behavioral part of Verilog, one of the structural IR, and one more for the netlist level. We added a front end from Verilog to this IR, some blurrings, a simulator, and pretty much what we wanted to build is something that looks like LVM, feels like LVM, but for hardware. This project was actually started before MLIR even existed, but very, very quickly we moved into using MLIR for this kind of toolchain. So no need to really fully understand that IR here, but given a piece of Verilog code here on the left, you take the Verilog code, you move it through Moore, our front end, into our IR stack. And we just keep optimizing this IR with classical compiler transformations. The objective or the metric being here, eliminating all control flow to at some point have only straight line code that you can synthesize in hardware. Right? And in fact, you just use classical compiler transformations, slightly different parameterized, to simplify the code. Further and further now, all the branching is already eliminated to eventually get an optimized version of this Verilog code. And I found that quite impressive, because for me, hardware design was so different. But if we actually look at the IR, if any one of you ever looked at compiler IRs from the LVM ecosystem, this thing looks incredibly familiar. This is all SSA. You have certain operations that return SSA values. The types are slightly different. We don't have integers. We have signals of type integer. We now drive and probe integers, or these signals, rather than load and store from memory, but kind of conceptually. This is actually quite familiar, right? So I would say that this is really the same kind of game to play. Kind of like maybe someone bought an extension package. But beyond that, if I understand the like meaning of these operations, I am actually quite qualified to write optimizations, transformations, and play that game, right? So yeah, we optimize it. And what initially was LLHD turned out to become an LVM subproject, now called Circuit. We're together with like Microsoft, Sci5, Xilinx, and many other people. Many more abstractions got built. Here you see the original part of LLHD. So some of LLHD still exists. Sequential and combinational logic, in fact, can be shared with a lot of the Sci5 toolflow now. And a newer project that some of my students and collaborators are building currently is called ARC, a simulator for Verilog, and currently mostly Chisel, actually. And again, it's really a nice kind of interesting tool. It combines Verilog at the front-end side, in this case with LVM and like low-level compilers at the back-end side, to generate high-performance code for hardware designs. If anyone is interested in Arculator, it's all part of Circuit, it's all open source. The tool you would compare it with might be Verilator, which is a leading open source hardware simulator. Arculator is slightly different in the sense that it has more IRs in the middle, exploits more structural information. The key difference here is that a typical Verilog model or module is organized in terms of like the structural concepts humans think of with respect to hardware. Right? There are certain hardware units that need to be combined to implement a certain microprocessor. For a simulator, this kind of semantic meaning is not as helpful. For a simulator, what you really want to know, what are their register transfers? What is the combinational logic that needs to be executed between two registers? Right? So you really need to revamp the entire design to make that more explicit. And that afterwards will facilitate or makes it a lot easier to simulate fast. There are a couple of performance numbers, so we are more or less on the same performance than Verilator, slightly slower than Ascent, which is another specialized tool in that space. Our compile time happens to be a lot better, because Verilator, what it does, it works on the AST of both Verilog and then generates C++. So that's pretty much a really great idea, 20-year-old software project, but I think the abstraction it's using are maybe slightly unflexible. And so if we are doing that for Rocket, for newer versions of Rocket, Ascent doesn't work, unfortunately, but kind of otherwise the trend holds. And so, I mean, this is still a young project, but maybe that could be a component towards like a more open source hardware design ecosystem. We also have some people working from a verification in Circuit. So we have a relatively small core set of dialects for hardware, which we can again translate to our SMT representation, and then we can do equivalence checking or bounded model checking to do certain hardware verification tasks. Right? And again, I want to remind you, whatever I talk here about is pretty much just playing with abstractions. An interesting game we can play here is if we would have, for example, an intern invited who is a finite state machine expert. Then coincidentally, there's a high-level abstraction for that thing, and we could realize that verifying it directly with the SMT dialect might actually be more effective than going through a lot of low-level abstractions, right? And so these are the kind of some of these like small local games that we play individually, but that actually combine quite nicely as a team. And so I want to close this with the invitation for us to all play together with all the different games we could play. So one of our research associates is currently working on a distributed memory abstraction that we're about to upstream to the MLI repositories. I realized I very proudly put quantum computing into the title of this talk, and then I really wanted to make sure that at least I have it on the slides. So we just had a relatively minor work on introducing a quantum computing abstraction into the MLI ecosystem. Coincidentally, that abstraction actually has very similar properties to many of the hardware abstractions. So it's quite interesting. And there's also like, on our semantic side, we started to explore a little bit fully homomorphic encryption, which is, again, a really high-level abstraction. So you reason about mathematical objects that are way more abstract than a typical SMT solver query can solve. And so here, like working with an interactive theorem prover like Lean is quite helpful. So that's it from my side. I hope I kind of, at least personally, I find now I start to understand my research a little bit better. If any of you got a gist of like why we are trying to connect these things, I would find that a success for this talk. If there are any questions, let me know. Thank you.
Thank you very much. We've got time for questions. Stunned.
I see a question there.
I like this game semantics way of thinking, and I have sort of similar perspective in formal methods. But one of the problems is like, say in a normal game, that at each step there's only a finite number of moves you can make. Say with an interactive theorem proof like me, my next move could be any tactic I want.
Right. So, I mean, in general, I mean, kind of the game I play is, I mean, I think it's really hard to play, right, all these things. But I think one thing, especially from the formal methods side, that I think is a really interesting trend in the kind of compiler ecosystem, is really that we move away from this uniform IR, and we create very specialized high-level abstractions, right? And each of these high-level abstractions actually is a relatively simple game to play, right? And so the trade-off is rather having a Turing-complete program that can do pretty much anything, you move it into like more like a chess-like game on a certain abstraction level. So within a given abstraction, I think the games are fundamentally easier. Combining these abstractions together, I mean, it's still an incredibly complicated game to play. So I don't think, especially from the formal method side, I don't think there's hope for us to kind of like formally do like cover everything. But I think there are interesting seeds where we can bring formal methods a lot closer into the ecosystem than we have done before. Yeah.
So may I ask a question about how do you see the connection between the classical compilers and the electronic design of automation? Because I mean, like in my mind, the classical there is an interface which is the ISA between the compilers and the hardware. How do you cross that boundary?
So that's an interesting question. So the question was, how do I connect an actual compiler with a hardware design? Because the only really defined interface is the instruction set architecture, right? And in some way that is true, right? So typically that's how you connect the tools. But there are many other levels of synergies that you can exploit. One at the like purely like software architecture level. You can use the parser and the printer and a lot of the testing infrastructure pretty much uniformly across the projects. Like then having like connections to an SMT solver, that's a lot of stuff that you can reuse. Then a lot of let's say we write a super optimizer, like one of our students is currently writing a super optimizer. There's not a lot of difference between arithmetic operations and combinational logic. I mean, the kind of like operations you have are slightly different. I mean, you don't have they're slightly different, but not fundamentally different, right? And so rather than kind of building like this one deep connection, what I said earlier, like we break it into hundreds of pieces, and they still don't fit all together, but a lot of them actually do. There's an incredible amount of reuse if you make the pieces small enough. Yes?
Thanks for the great talk. Often these compilers are viewed as adversarial to the programmer because if there's any undefined behavior, for example, in the language, then the compiler goes off and it undoes the intentions of the programmer by middle range IRs, removing security checks, and then all kinds of optimizations which kind of are usually viewed as bad. As you're compiling forward, do you ever think that there's a role for some of the compilation processes to go backwards, back to the programmer, so that they can somehow warn the programmer when they're heading into undefined territory or other kind of more dangerous aspects of the compilation process?
So the question was should the compiler talk with the programmer rather than being a black box that does crazy stuff that sometimes is useful and sometimes incredibly dangerous, right? And the typical approach to I think most compilers is kind of this black box compiler model. That you say, I know how to develop a compiler, I define a very nice interface for the user, and the user better trust that interface. And if they didn't read the standard about undefined behavior, then they are on their own, right? But I think that model, actually, it still doesn't work, right? At the moment you want to performance optimize code, I mean, the first thing people will do, they write inline assembly. I mean, if someone is really ambitious, they start to change the compiler, and then pretty much you hack around the fact that this boundary really is not working if you want to performance tune code. And so my maybe a slightly radical approach is we should give up that barrier, right? There's another solution. We can actually, I mean, not everybody wants to dig all the way down into the compiler, but I mean, rather than enforcing a very strict barrier and pretty much, I mean, I think it makes a lot of sense to build automation and tooling that makes these interactions easier. And then if people actually choose that path and choose to dig into parts of the compiler, maybe that's easier. And so introducing formal methods is a way to then make sure that students don't break too, anyone doesn't break too much of the compiler. Some of our Python tooling is a way to inspect or make compilers more accessible. Anything that I propose, I think, is very, very preliminary and broken. But I think there's a benefit of going towards building automation that makes that process easier, rather than building automation to prevent that from happening.
It's also not fair to blame the compiler on undefined behavior, right? Sure, compilers abuse of undefined behavior for optimization purposes, but it's the language's fault for creating undefined behavior.
Right.
Yeah, but I think the question, though, was about to what extent is the poor programmer warned because they may not have read the language spec in great detail.
Yes.
And basically, because really you want the programmer to have a bit of a slap over the wrist, saying, no, don't do that, you should do the following instead, rather than you end up with some random behavior in the executable.
But we have those kind of remarks already, right? So you're like, oh, you're trying to read past the pointer or something, right? So that this is a more high-level AST analysis than actually the compiler, because the compiler in the end looks at IR and says, this is a pointer, I'm reading it, I have no idea where it came from, I'm just going to read it. Here you go.
Yeah.
There's a question at the front.
Yeah.
So, yeah, just one thing. So, I don't know if you know, Bartosz Moniewski, so he has this blog post on basically sort of maths is your assurance policy. He claims that, sort of compilation will essentially, AI-driven compilation in, I guess, the same sense as the compilation game would sort of essentially become good enough that, the task of assembly writers has basically been abstracted and optimized away, but the task of C++ programmers and the like would also get abstracted away. And sort of, he claims, A, that eventually a compiler automation will get good enough that happens, and B, that essentially the remaining DSL, the final sort of declarative layer that you reach, essentially would be category theory. He says something like, category theory is the insurance policy against the drying up of your current watering hole.
Okay.
To what extent do you agree with both of those claims?
I think that's certainly a very opinionated claim, I guess. I mean, I don't know. But I think from a more practical perspective, I think obviously there will be a lot of automation. I think the problem with a lot of automation is that you stop understanding it. And it doesn't really help you if you have an incredible amount of automation and it works 95% of the time, right? That's not scalable. So I think a lot of the challenge is to kind of see how, and I mean, even assembly programming is not redundant, right? It's redundant for most people until it's not anymore, right? Until you actually need it. And then it's really painful. And I don't think like adding a lot of automation into the tool, building up further barriers of people accessing the low-level details will kind of lead into a kind of, give us a nice integrated ecosystem. I think you want an integrated ecosystem where you can have the automation if you want to, but where you pretty much can go all the way down and change something and actually maybe help the automation or the automation helps you. Like it needs to be a game, right? You want to do that together. Yeah, maybe in some way. Cool. I think a last question and we are at the end.
I wanted to ask about joining these a compiler for electronic design automation with some probabilistic system. The reason I'm asking is, for example, in power electronics, it's very difficult to figure out how to minimize capacitance between components.
Yeah.
And there's no analytical solution for that, so you need basically to sample a big map of combinations.
Right.
Is that possible to be integrated as part of the compilation process or as part of the verification process?
If that's an existing question, maybe. How to do it, I wouldn't know. But I think it's an interesting conversation. Like I didn't think about it.
In
But
a sense, can you have probabilistic output with the same input? Can you generate multiple different configurations for compiled design?
I don't know. But I think actually a lot of what I presented is probably quite useful in that space. Like a kind of like having a really generic, abstract, structural. I mean, in some way, whatever we touch here, it's sufficiently structural expressed that you can interface with it nicely. And so I mean, seeing if you can use probabilistic methods to kind of like do something interesting is probably possible. But yeah.
So this
Albert, I think we.
Just to comment, I mean, there have been probabilistic programming languages and also ODE type of programming languages for continuous signals using very similar frameworks. Like think of SSA on streams.
Yeah.
There are papers on this I can give you some.
Okay. Cool.
So the answer is yes.
The answer is yes. Excellent. Cool.
Well, we should draw things to a close. I think we're out of time, so we should thank Tobias very much.
Thank you.